because it turns out that the A's, if the part that's being pumped, you know what the length of it is, right? It's less than or equal to N. So you cannot pump the two parts of the A's, the two distinct parts. So if there's pumping that occurs, and it's going to include some A's, it has to either be the first set of A's or the second set of A's, but not both. So what'll happen is the A's will get out of balance. All you gotta do is set I equal to 0. And if it's got B's in it, it's either gonna be the first set of B's or the second set of B's. Or if you set I equal to 0, the B's get out of balance. If it includes A's and B's, it's still the case that it can only be from one subsection of the A's and one subsection of the B's. Set I equal to 0, and now you're out of balance twice. But what you need to do is just say, well, if it includes any A's, don't even worry about if it's got B's. And then you do the other one and say, hey, if it includes any B's, and then you can say if it includes any A's, it must either be from the first collection of A's or the second collection. I'll set I equal to 0, and the number of A's won't match. And you do the exact same thing on the B's. So try to find an approach to these that doesn't get you into tons of cases where you start saying, well, what if it's over the first A's? What if it's over the first A's and B's? And you get into that, and then you start saying, well, sometimes it'll get the A's and B's out of order. I don't care, because you can do it so much easier not worrying about those sorts of things. And I won't give you any problem where you have to worry about the order. If you're sitting there and you're analyzing it, and you're doing something that you say, oh, that forces them to be out of order, then you're doing something more complex than necessary for the problem that I give you. I don't want to say that there aren't problems that require you to do that. I'm just telling you the ones I give you, there'll be approaches to it where you can assume that reordering is not going to occur. So if it's over A's and B's, then what your assumption should be is that the A's, it's U, V, W, X, Y. V and X are repeated. So one of the cases, if it's over A's and B's, then the A's can be the V part, and the B's can be the X part. And in my case, there'll be nothing that's more complex than that. Okay? That doesn't mean I won't have C's in there. It might be, because I could have, what's the problem you have? Well, I have one later. I'll show it to you. Okay? I am going to ask you to write one grammar. Context free. Yes, sir.
How would the number of cases relate to the number of Neil cut?
The number of cases relate to how you attack the problem, Dave. Now there's some where you typically, like let's say I had A to the N, B to the N, C to the N. How many cases do you think that would take?
So I did 5, but
okay, that's one.
But
how about
3, 4,
2?
and 5
How about 2 cases?
Unnecessary, so just
Yeah. How about 2 cases for that one?
Okay, so
Assume that it contains either A's or B's and no C's. Okay. And A's and or B's and no C's. So it might contain some of each. And then all you got to do is set I equal to 0, and you're either reducing the number of A's or the number of B's, or perhaps the number of A's and the number of B's, right? But they won't, whatever gets reduced won't match the number of C's. So I've just taken care of that possibility. Now I do the next one. It could contain B's and or C's.
So that and perhaps kind of covers both cases.
That covers, that right there I've covered every possible case.
Thank you.
So you try to find ways to attack it to reduce the number of cases. That's not to say that you can't get it right with 5 cases. It's just that you're putting a lot more work on yourself. So usually you try to figure out how to attack the thing in a small number of cases. This one, I went over this grammar with you. Did anybody have a question of it? It's the one, I just love this one. I can't help myself. But the fact that this language that looks so complex and is so complex, WW, if you take the complement of it, it's not complex, it's context-free rather than context-sensitive. And it's the distinction between having to match up everything versus making one mistake. And that occurred twice in the semester. Where's the other place where we had that? Well, we didn't do a formal proof. Traces. A trace that is a legal trace has to be right at every step of the trace. Something that looks like a trace and has a mistake, how many mistakes does it need to have? One. And then it's an invalid instance of a trace. So we did it twice. The other thing is, what is it, if it has to match everywhere, what would be the quantifier associated with that? Right. And if it has one mistake, there exists. And almost always when you look at problems where you can describe it as a for all versus the there exists is easier than the for all. This was an example I gave you as just as a sample problem. So I wanted to throw it up there. And it's the one where we've got two sets, S and T. S is RE, non-recursive, and T is RE, but it might be recursive. So I can choose a decidable set for T. I cannot choose a decidable set for S. And what I'm interested in is the set of Z such that Z is equal to X plus Y, where X is a member of S and Y is a member of T. Did I go over this with you before? Yes? Okay. So I'll just mention it again. You know, if can it be non-recursive? The answer is no to it, because you actually can enumerate all of the elements of this thing quite easily. By the way, what if I gave you times versus plus? So since I went over this, I'm going to change plus to times. Can that be non-RE? If the sets S and T are both RE. Yeah.
Can you explain again what RE means?
And that means you can either semi-decide it or you can list it. There's an algorithm that lists it, or there is a procedure that semi-decides it. That's called RE.
Okay.
And the reason it's got two definitions is that they're equivalent to each other. Just like NP has two definitions. One is that it is the set of algorithms that can be solved in non-deterministic polynomial time. But the other definition is it's the set of problems where you can check a solution in polynomial time.
Okay.
And they're equivalent to each other.
Right.
So this one has two equivalent ones. Either it is the domain of a partially computable function, or it is the range of a computable one. The problem with the range one is that only works for non-empty sets.
Okay.
So what you do is you say it's either empty or it's the range of an algorithm. Or alternatively, it is the domain of a procedure. Because realize a procedure could diverge everywhere, and then what would it be its domain?
Everything.
Nothing.
Oh.
If it diverges everywhere, its domain is nothing.
So what is, like, typically when you think domain range, you think like a function, right?
Yeah, and remember in recursive computability theory, domain is the set of values on which the function converses.
Okay.
Okay. Range is the set of values it produces, so domain is a little different. When in this field you talk about a universe of discourse, which could be the natural numbers of my input. That's the universe. But the domain is the ones that I sort of like because they actually produce an output from that.
Okay.
So,
That makes sense.
yeah. Okay. So if I change this plus to a multiply, what it would say is this is how I can enumerate the set. This is the enumerating function that is for the set S. This is the enumerating function for the, oh God. This is the enumerating function for t, and that's s. Sorry about that. Doesn't do any good to have it for the same, it doesn't matter which one here. What did I call them? Fs and ft. Why I had a G there, God knows. Okay, there we go. It would actually allow me to save it without complaining. That's shocker. Okay, so what this does is it says, you give me a pair of numbers, which is a single number, but you have a pairing function, and I can extract the numbers from it. And what I'll do is I'll pick the x value in the set S, and I'll add that to the y's value in the set T. And that will be in the set E. And since this is for all pairs x, y, this will get me all possible values that are in the range of Fs, and all possible values in the range of Ft, and all combinations thereof. So if I said multiply, all I have to do is alter that and make it a multiply operation. And that would give me the product of any value that's in S with any value that's in T, and all possible. But I had to make one little thing up here and say T can't be empty. Why did I not have to do that with S? I said S is non-recursive. The empty set is decidable. So I didn't have to worry about S being empty. It can't be empty. But I said T could be decidable, in which case I have to worry about the possibility if it's empty. But if it's empty, what is E? Empty. Because if you add all the elements from the empty set with another set, you get back the empty set. Because there's nothing here to do the, if you do the product, what do you get back? Nothing. Yes, David?
What does olive represent here?
Pardon me?
What does olive represent here?
Oh. Natural numbers, where do I have it?
Bottom lines, the middle.
Oh, yeah, that's the set of natural numbers. So, in the case of addition, what I did is, since T could be decidable, I made it 0, the value 0. So what do you get? You start with S, you add 0 to every element in S, you get back S. So this would be an instance of RE. What would you make T if the operation was multiply?
1.
Right? And then you'll get back exactly S. Okay. Now, in the case, can it be recursive? What I did is I said, yes, just make, so I could make T empty. That would have worked. So I wanted to give you an example. What if I said to you, T cannot be empty? What if I declared that? If I declared T cannot be empty, then I need to find an alternative. The set of natural numbers is an alternative because once you add the minimum number from the set S to 0, then what will you get beyond that? You'll get that value plus 1, that value plus 2, that value plus 3. So what you'll get is every value greater than or equal to the minimum value in S. What could you do if it were multiplied? Can it be recursive? How about if T is 0? And you get back 0 from that. So there is a way, they're slightly different in the attack on this.
So we just have to give an example where it can be recursive.
That's right.
So why in A, you say.
It cannot be non-RE. That's why I had to do more work on that one.
I see.
So if I give you some property and you've got to determine, you want to show me that it cannot be something, then that requires a constructive proof. If you want to show it can be something, it requires an example. And that's typical of, and improves, what we tend to do is actually the somewhat similar to that. If somebody asks you to prove something or disprove it, what do you do to disprove it?
Make sure I counterexample.
Yeah, right. So this is sort of the flip of that. You show an example if it's true, and you show a proof if it's false. Whereas in your typical courses you take in discrete math, you show a proof if it's true, you show a counterexample if it's false. This tends to put things on its head occasionally. Okay. This is, oh yeah, I did not, yeah, I did, okay. This is the key for assignment 8, and this was just, what I was asking you to do is reduce halt to repeats. And repeats is just that somewhere there are two distinct inputs to this function where it produces the exact same value. So that's all it amounts to. So what I do is I just take and I say, hey, I'm starting with halt, so I'm given an f and I'm given an x, and I know it's in halt if f of x converges. So all I do is compute f of x minus f of x, and I do that for all y in my new function. My new function will not only repeat, it will repeat constantly if f converges on x. What will it do if f doesn't converge on x? My new function will diverge everywhere. So it won't have a repetition. So the idea behind it is it either repeats all the time or it never repeats, because I don't consider divergence to be a repeat. It has to be an explicit value. Next one is to show it's no harder than halt by reducing repeats to halt. So the way I did that one is I said, I'm going to create a function. So I'm assuming I have a function that might have a repetition in it. So all I'm doing is an enormous search here. And I say, I don't really care what value of z you give me. It doesn't matter to me in the least bit. What I'm going to do is I'm going to end up trying every possible value of x, y, and t. And for those values of x, y, and t, I will check to see if it converges for x and y in t steps. I check to make sure x is not the same value as y, and I check to see if the values are the same. And the only time this will be true is if there's a repetition somewhere. What will happen if there's not a repetition? It will diverge. So what can I tell you about my new function? It actually converges everywhere. Or what does it do? It diverges everywhere. If it converges everywhere, what values does it actually give you? I don't know. It's whatever this x, y, and t are. But actually it's not. Why? It's a predicate. What does a predicate give you back? True or false? So this thing will give me a 1. Otherwise, it diverges. Now it turns out if it is, I have actually reduced what to repeats. What have I actually done here? I reduced repeats to what in this one? Not just to halt, but to total. But if a function's total, what do I know about it? It halts on all input. Just pick a bloody input and ask it. See, this shows it reduces to the halting problem, but it also reduces to total. Are you surprised it reduces to total if it reduces to halt? Why should it not surprise you? Because total is more complex than halt. Does this mean it's as hard as total? That it reduces to total? No, it means it's no harder. Why do I know it's not as hard as total? I showed halt reduce. I showed that halt reduced to it. And I showed it reduces to halt. So what is it really? Its complexity is the exact same thing as halt.
So does that mean they're both RE complete?
Yes, they are both RE complete. And in fact, I am never, ever going to give you a problem that is undecidable in RE that's not RE complete. Why am I never going to do that?
Can you think of one?
Because you'll probably never, yes, I can.
Okay.
But they are so bizarre.
So I can't.
The functions that are not RE complete, but are RE undecidable, are so bizarre that there's no way I could ever ask you a question like that. It can't happen. Any problem that is a rational problem that I can come up with that's RE undecidable will be RE complete. They'll all be that. So I will guarantee you won't get any middle ground in there because they're too bizarre. But there happen to be an infinite number of them. They're all over the place and they're all bizarre. Yes?
Could you explain what you mean by RE undecidable?
That means that, see, every decidable problem is RE, right? Okay. So an RE problem that's undecidable means that it is semi-decidable, but there is no algorithm to solve it. Okay. Clearly, the halting problem matches that. That is RE, and it's undecidable. Okay. Then there's these ones that are decidable down here. There's actually a lattice. If you start with the one at the top, there are actually two problems that are unrelated to each other that reduce to the halting problem, but are not as complex as the halting problem, but they're not decidable. We're never going to do this, but just so you know, and you know about those ones, there's a lattice under them, and there's a lattice under each of those. And there's this strange structure, and you know what happens eventually? When I say it's a lattice, what that means is, give me two incomparable problems, there'll be one problem that's harder than either of those two, and there'll be one that's easier than either of those two. This is what does that look like? A nice lattice work fence, right? If I repeat that all down, and at the very top is the complete one, and the very bottom are the recursive problems. So there is a top and a bottom to the lattice. But there's actually an infinite number of nodes in there. And the only ones we're ever going to deal with is the very bottom, they're decidable. The very top of the RE ones, they're equivalent to the halting problem. Okay. Those are the only ones we look at. But we know there are problems worse than that, right? Total is worse than RE. It's harder. Okay. What do we know down here at the recursive ones that we dealt with the last 3 weeks of the semester?
Decidable?
They're decidable, but what about decidable problems? Did we see a hierarchy in there? We had the polynomial, the P, and NP. So we were looking at those that were solvable in polynomial time and those that took non-deterministic polynomial time. So there's another hierarchy down there. Is it more complex than what we? Oh, yes. I mean, there's an actual nasty hierarchy among the polynomial solvable problems, and it doesn't even have to do with the degree of the polynomial. Okay. So there are all sorts of nasty things. We're not doing those.
Can we look at the sample question number 5 again? Briefly?
Yeah,
For part B,
yeah.
non-recursive means non-decidable, right?
Non-recursive is undecidable.
So, but wouldn't S plus 0 be decidable?
No, because it will be S. And S was declared right up here to be an RE non-recursive set.
How is a set non-decidable?
Oh, it could be halt. So let's say S is halt, which is the indices of programs and input to programs such that that program halts on that input.
But isn't halt like an algorithm?
No, halt is a set. Halt is a set, and the algorithm you seek is a solution to membership in the set, and there is no algorithm that can solve that one.
Okay, so
Okay.
that's only undecidable because S.
Because S is undecidable, that's
If-
right.
If S was not declared that way, then that would be,
That could be whatever the complexity of S is, whatever it is,
okay.
okay? So if S were total, which is not even RE, then S plus the set 0 would still be S, and that would be total, which is not even RE. So if I declared that, then it would be really nasty.
Okay, so that would be not recursive still.
No, and not only, the non-RE are not recursive,
Okay.
they're worse than RE.
Okay.
So like total, you cannot even, see, you can semi-decide an RE problem. You cannot semi-decide things that are worse than RE.
Right,
So like total has no semi-decision procedure associated with it.
okay.
And why? Because it's got that bloody for all sitting out there.
Uh-huh.
And whereas halt has just a there exists. So, yes,
Sorry, since we're talking about that real quick, non-RE means you can, RE means you can list them, but it might not halt on the problems that it doesn't.
if you know what that means, the list is not gonna include the things that aren't in the set. So just being able to list them doesn't help you, because if your item doesn't show up for 1 billion steps, it doesn't mean it won't show up later on. But the other way to look at it is if you can list it, you can semi-decide it, which in itself is not a decision procedure, because a semi-decision procedure can run forever if the answer is no. But the problem is you don't know it's running forever even after a millennium,
Yeah,
because it might converge after that period.
and non-RE is the flip of that statement.
Non-RE are the ones where you cannot even come up with a way to list the elements, and you cannot semi-decide them.
I thought it was you can list the ones that you know the end, okay, sorry.
No. Non-RE means you can't even do that.
Okay.
Okay. So total is such an example, and it's always, the non-RE have a for all somewhere in them. Now, the complement of halt is actually not RE, it's co-RE. Complement of halt means, if you think of the complement of halt, that means that it diverges the set of fx such that f diverges on x. There is no semi-decision procedure for that.
That's what I was thinking.
Yeah.
Mixed them up.
Okay, so here's one that just